in our problem-solving procedure, we want to start with the information that's given to us that might not be in the free body diagram. So looking here, what information, or it may also be in the free body diagram, we can have it in two places, that's okay. So what do we have to put in our given? Right, so W is the weight of this cart as indicated on there. So right, I can put it also here, and that's okay. It will be in the free body diagram too. So K has a value of 5 newtons per millimeter. The cart weighs 100 newtons. They do tell us the contact between the wheels and the ground is frictionless. We could put that in the given, but that's going to be reflected in the free body diagram as well, as we'll see in a minute. The spring is unstretched when delta is 0. That's going to always be the case with our springs. All right, so our spring constant, that's important, and W will appear in a minute in our free body diagram. All right, so that's given information that we'll need in our equation step. What do we need to find in this? Right, that lowercase delta, the stretch or the deformation of the spring. So we need delta for equilibrium. Right, so remember, the way I'm using delta here, delta is going to be positive if we're in tension, negative in compression. And then we can always use that same equation for Hooke's law, that's our current length minus the unstretched length. And then that way, always positive is tension, negative is compression. All right, and then we have the free body diagram step. So this is where we need to choose the thing we're going to treat as a particle and draw all the forces that act on it. So in this case, what can we choose as our object of interest or our particle of interest? Right, we want to choose the cart in this case. The cart is going to be affected by its touching the spring. It's going to be affected by gravity. In this case, we do need to account for it because they tell us the weight of that cart. And then there'll be other forces as well. So the cart is going to have all the forces acting on it concurrently, and that's what we're going to model as our particle of interest. All right, so I'm going to use, I think it matches my notes here. I stuck with an XY coordinate system, X right, Y up. Although in this case, because we're at a slant here, it actually might be useful to use a rotated coordinate system, but I'm not going to get into that right now. So as far as kind of construction lines, X is right, or X is horizontal, Y is vertical. But because we have an incline here, I'm adding another construction line that's going to be 20 degrees down from X. And we'll see why this will be useful in a minute. All right, so what are the forces that act on our cart? Right, there's going to be the spring force, because potentially the spring is going to be stretched, although it could be compressed, but physically it would make sense if it was stretched here. So the spring force is going to act along the direction of the spring, which in this case the spring is parallel to the incline. So the spring force will be acting along this 20-degree line. Now a couple things here. Again, this is at 20 degrees. We don't know what the force in that spring is at the moment. So we need to give it a name because we don't know it's 50 pounds or 20 pounds or whatever, or this is in newtons, 20 newtons or 50 newtons. It doesn't really matter what you call it. I'm going to call it F sub k. I find it helpful to put that k subscript to remember that it is just a force, but specifically this force is coming from a spring. And that k kind of reminds me, I'm probably going to need to use that later with Hooke's law. But if you call this S or just F, that's fine too, as long as you're consistent. The other thing to keep in mind here, or to note here, is that I am drawing it pushing away or coming out from that point. This is the assumption of tension. I'm assuming that this spring is pulling up on this crate. So I'm drawing it up and to the left. So that is going to be consistent with my assumption of tension, which will be reflected in my equations in a little bit. If I had this down and to the right at my point, I would be assuming that the spring is in compression, which is okay as long as I'm doing that consistently. Again, I want to reiterate, I always assume tension. I think it's much easier to do these problems that way, but you don't have to. What other forces act on the crate? right? The weight of the crate. Here, this is why I did keep y vertical. The weight is always going to act towards the center of the Earth. So the weight of the crate is going to be pushing down in the negative y direction, and we were told that it weighs 100 newtons. Newtons is already a force, so I'm going to leave it like that. Pounds are force, newtons are force, kilograms are a mass, and only if we have kilograms do we need to convert it to newtons by multiplying by gravity. Right, and then what other force acts on the crate? Right, the normal force, so the force that prevents it from falling through the inclined plane. What direction will the normal force be directed along? Right, perpendicular to the spring, which is also, more importantly, perpendicular to the surface. Normal forces are always perpendicular to the surface, and they can only push, they can't pull. So that inclined plane is pushing on the crate, so it's going to be an arrow pointing towards the crate from that normal force, which I'm going to call N. It's perpendicular to the surface, which means that if the surface makes a 20 degree with the horizontal, the normal force is going to make a 20 degree angle with the vertical. All right, so these are all three forces we're accounting for. They're acting on the crate. We're not accounting for air resistance or air pressure or anything like that. These are the major things that impact our crate. So now we can go to the equation step, and we can write, first of all, the equilibrium equations that come from the free body diagram. Again, I'll take one step back here. I chose x right, y up because usually it's the easiest. But another option would be I could have a normal and tangential coordinate system. So I could have said that this was like the n direction and this was the t direction because those are also orthogonal to each other. And instead of summing forces in the x, forces in the y, I could have summed forces along the normal and summed forces along the tangential. I'm not going to do that now, but in the future, sometimes that does make the algebra easier. Our results will be the same. Did you have a question? All right, so I'm going to stick with x and y for this example. All right, so first equation, my equilibrium equation, I'm going to start by summing forces that act in the x direction. All right, looking at the free body diagram, there's three potential forces that can be in this equation. First, I look at the 100 Newton force that has only components in the y direction, so none of that acts in the x. So this will not appear in my equation. I'll go to the normal force next. The normal force is going to have a horizontal component that points to the right and a vertical component that will point up. So the normal force, its component in the x direction is pointing along the positive x-axis. So it's going to be positive n. And then if we look at least how I'm measuring this, if this angle is 20 degrees, the horizontal component, or the x component, is opposite the 20. So according to the way that at least I've drawn my, indicated my angles here, it will be n sine 20. I should also note, I didn't know up front what the force in the spring was, so I gave it a variable name. I also don't know what the normal force is. And then a component of the spring force, again, the x component here points to the left, and the y component is going to be pointing up. So for the spring force, it will be a negative Fk, and its component is going to be, according, from the vantage point of the 20 degrees, it's adjacent. So it's going to be Fk cosine 20 degrees. If I look at this, I have two independent equations, and I have two unknowns here, n and Fk. Had I used a normal tangential coordinate system, algebraically by hand, these would be easier to solve, but the setup, you have to think a little bit more carefully about the angles that you're using. But this is solvable, two equations and two unknowns. So because this is right now solvable, I'm going to take advantage of that and solve them using substitution most likely, because I can find n in terms of Fk, put it into equation 2. So if I do that, I get that n, solving equations 1 and 2, n is 94 newtons, positive, which it has to be, because it's a normal force, it can only push. And the spring force, Fk, is 34.2 newtons, also positive, meaning that our assumption was correct, that spring is in tension. All right, so I have the normal force, I have the spring force, so what's left to do? Right, so remember, this is why the find part is important. Our mission was not to find the spring force and the normal force, although we will need them along the way. We need to find that delta, which so far is in none of our equations. So we're not done with the problem. We have to come back to our equation step because something here has to involve delta. And this is where we can use that equation that's not from equilibrium, but comes from Hooke's law, that the force in the spring is going to be equal to its spring constant times its deformation. Right, so these two came from free body diagram. This comes from Hooke's law. Now, I could also write this as K times L prime minus L naught. But in this case, we don't know how long the spring is originally, and we don't really care. We just want to know how much it's stretched, because that's how far this cart has gone downhill from its initial position. F sub k we just found was 34.2 newtons. The spring constant here is, I want to be careful here, I'm going to call this x tilde just so I don't confuse them. The spring constant in the spring is actually 2 times k, where they gave us k as 5 newtons per millimeter, which means that the spring constant is 10 newtons per millimeter. I know Fk at this point. K I can find, so the only thing I don't know is delta. So I can now solve equation number 3. I will leave it here in, so I have newtons, I have millimeters. So delta must be in millimeters for my units to match. So solving equation 3, where I can divide 34.2 by 10, I'm going to get that delta, the deformation in the spring, is going to be 3.42 millimeters. Or 3.42 times 10 to the negative third meters, both of which would be acceptable answers for me for this class.